So Sarah, I'm just going to make you a co-host as well, so you could keep an eye on who's
Sure.
coming.
Thank you. Do you want to do the Answer Garden thing up front today, Praveen, or not?
Yeah, that would be good. Thank you.
I'll do that when we're sure we've got.
Yeah, just in a
Bigger
couple of
number.
minutes when we've got people, yeah. Okay, just checking if this is okay. All that is fine.
They requested your latest.
Okay, hello everyone. Thank you for joining today and welcome to this webinar. And my name is Parveen, Professor Parveen Ali. I work at the University of Sheffield and Doncaster and Bassetlaw Teaching Hospitals as Professor of Nursing and Professor of Gender-Based Violence. And I have got Sarah Gardner with me, who works at DBTH as a librarian, and both of us do these webinars every month on different topics related to research and publications, mainly for healthcare professionals who are working in NHS and especially DBTH, STH and university, but we usually keep it open so people can join us from all around the world, and we try and accommodate as much as we can. So today's webinar is an interesting one where we wanted to talk about use of artificial intelligence in healthcare setting. And when I looked at, there has been quite a lot of interest in on this webinar, and the registration number was going up and up and up. So then I thought that let's try and find people who actually know much more about artificial intelligence than myself and see if they would be able to talk to us. So I'm very grateful that Professor Ashik Anjum from University of Leicester has joined us today. So I'm just going to introduce him and then he can tell a little bit more about himself so that we could understand. Professor Anjum is a professor of distributed systems at the University of Leicester, and he's also Director of Enterprise and Impact for the School of Computing and Mathematical Sciences at Leicester. And his area of research include data-intensive distributed system, distributed machine learning model, self-adopted features, digital twins, and physically informed machine learning. And I will stop there because I don't know half of what it means. So I'll leave Professor Anjum to explain it. This session is recorded and also streamed on YouTube. We do this mainly for people to help understand, for people to have a look, go back and have a look at it, and to also to give it to people who have registered but were unable to attend for some reason. So I hope that is okay with everyone. What we are going to do is talk for about, Professor Anjum has decided to talk for about 40 minutes, 45 minutes, and then we can have question and answer. So in between, if you have got any questions, I would suggest please keep a note of that or keep writing into the chat box, and then we can come back to those questions. So I hope that's okay. Sarah, you wanted to say something about Answer Garden?
Oh yes, thank you, Parveen. I've put the link to our Answer Garden in the chat. If you wouldn't mind visiting and give us your job role, if you see a job role similar to yours already in the sort of word cloud that's forming, then just click on that and then it will add you again. But we get a feel for the kinds of professionals that we're reaching with our webinars. Thank you.
Thank you. And without further ado, I will go to
Yes,
Professor Anjum and he can start. Thank you for joining us, Professor Anjum.
Thank you, Professor Praveen Ali, for inviting me for this interesting audience. I have been doing similar kind of work, working with different hospitals, healthcare, with healthcare professionals, with pharma companies. So I would be giving some examples that how AI means to medical fields in a broader context. But but I would be starting with more or less a wider context, because I have been also working with a number of other domains. And as we say that this is to some extent an interdisciplinary learning, so as other disciplines are learning from life sciences and medical fields, so why not medical sciences and life sciences should learn from the developments in other domains, actually. So there are many interesting examples that I would be giving. So right from security to engineering to a kind of environment. And obviously, I would be covering a few examples within the life sciences domain as well. So the way
You've muted yourself.
okay. So, but the previous discussion you could hear is right?
Yes, yeah.
Okay, so it's not allowing me to move slides. I don't know why.
Do you want to reshare again, or?
Let me see if, because as well. Yeah, I can do that. Yeah, so here, this is an outline of my talk. I will be starting with a few examples of big data, that why we need an AI in the first instance, or AI model in the first instance. And if people need AI, then what are different types of AI? And I would be starting with the distributed AI, because the size, scale, and the volume of data means that we need a different type of AI. Then I would be discussing different AI models people are using right now. Just to give you an example, ChatGPT is one of a distributed AI model. That's a large scale model. I would not be spending a lot of time on ChatGPT or similar kind of things, because I would be discussing the principles behind that. So, and then I would be giving you a little historical tour, so that AI is not new, that has been here for the last 30, 40 years. People have been using classical centralized AI analytics. And then this people also started using statistical and deep learning, and then now people are moving towards edge enhanced learning or edge intelligence. And then I would be then setting the foundations of for next few years. That's the current focus of most of the AI people are doing, and we say is edge AI and contextual adaptations. And here I would be briefly touching upon digital twins and how AI is going to inform the next evolution of AI models. So in a nutshell, I would be starting 20, 30 years in the past and would come to present literature and developments, and then would move into the future. So anyone both doing classical as well as more current models and AI would be able to benefit from this talk. So I would be starting with this particular slide. So this is an the Economist article. This is that the data is the world's most valuable resource. It's no more the oil. It's basically the data. So the difference between the people who have access to the latest knowledge or information is essentially the availability of the data. So previously, people used to say, in 20 years back, there was a big term known as digital divides. People who have access to the latest information and communication technologies, they think they are fairly advanced, and countries or regions or group of people who did not have access to the modern kind of ICT networks and the communication tools, we said that basically they are digitally behind, and we said that this is a digital divide. Now the same thing is happening with the data as well. So people who have access to a large amount of data, we said they are basically very resourceful, they are rich. And people who don't have access to the data, we say is that they are basically kind of behind the curve actually. So and especially the AI war is just started. So people who collect data, they would be the one who would be using it to develop services and models that would be futuristic, and then obviously they would be monetizing that and getting benefits. So behind all AI models, the story starts with the data. If we have the data, that it means that we could train model and get something that other people don't have. Just like in a gold, we could only mine something when there is a kind of traces of gold in a certain locality. So, and the data is to some extent that. So AI simply polishes, it refines and improves what is in their data to find something that other people don't know, and then basically we could sell that, or we could get value of that. So, having said that, so just to give you a few examples of where the data is coming and what are the sources of data. This is one example of data that people are talking about. So in broader context, for example, in the UK, there are 6 million cameras. This is an old number. They may have gone to manifold actually. And every person is to some extent videoed 200 to 300 times a day. So each of that object, when it passes through the camera, we say basically either the photo or the video is captured. Now just think of a scenario that the 6 million cameras are streaming data to a data center. So, and previously there were thousands of people right in airport control rooms or National Highway Agency or other kind of infrastructure providers that are looking into individual video streams and trying to find that is something is suspicious, anomalous, or that essentially not in line with the rules and regulations. Now, this is one example where AI is kind of facilitating that people don't need to sit in a large number of control rooms. Rather, AI would be able to automatically process objects and see that, by the way, if they are looking for a red car, AI algorithm would be able to look into all those 6 million streams in every minute or second and see that, by the way, that is the car, and that's basically in that particular location. So this is one example. Now, here, there is another development happening, and people say it's basically camera is just an IoT device. IoT is essentially where the digital and physical worlds meet together actually, or interact. So camera is just one example of IoT device. There are many other devices. For example, in buildings, we could see that there are sensors, for example, on highways, on motorways, and in many other examples. For example, I give you another examples here. So, for example, an aeroplane is essentially one example of internet device, Internet of Things device. So, and there are billions of lines of code, and each engine is generating 10 terabytes every 30 minutes. So, so here, for example, a flight from London Heathrow to John F. Kennedy airports generates 640 terabytes, and there are thousands of those flights. And on just one wing, there are 15,000 of sensors or IoT devices that I gave example in the previous slide, actually. So just think of the size or the velocity and the volume of data that we are acquiring. People are using it, for example, in this particular case, people are using it for kind of anomaly detection, for heat analysis, for safety, for navigation, other kind of things. So and any kind of developments that are happening here. So without AI, it would be very difficult to look into the health and the safety and the operational characteristics of a plane without the AI that the people are developing. So this was another example where we have both a velocity and the volume of data, and that is too big, that is beyond the capacity of the individual humans to process that. Now, this is another example. So we did this project almost 10 years back. This was a European Commission funded project. So here we were working with different hospitals, and for example, Great Ormond Street Hospital, London, Necker in Paris, Gazzolini Hospital in Genoa. So so here we were working with mostly children hospitals, and they had a lot of different data sets, either they are imaging data sets, lab data sets, genomics, proteomics, demographic, physical, and other kind of data sets. Now, this project, for example, we wanted to integrate the data and create an integrated database so that we can see that what is the impact of a particular scan or particular condition on the wider disease parameters and vice versa, actually. So here the idea was that we should be able to generate disease models, decision support systems, and use that basically cross modality information fusion, and use a kind of statistical model at that time, because this was more or less 10 years back, and there was no concept of these deep learning neural networks. Either more than 10 years. It was 2006 to 2010, actually. So it's almost 15 years back. So so here we wanted to do both horizontal and longitudinal integration of data. So, and just this was just 3 hospitals. It was so much challenge. Just think of a scenario that that if we have to integrate the data across all hospitals, because eventually that's going to happen. So we don't have the tools and the means to do that at a kind of at a scale, because due to different compliance reasons, ethical reasons, and then many other issues, that even access to data is challenging, let alone a kind of ability to process it. So there are a lot of kind of access issues, for example. So we produce a grid-based platform that can bring all these things together, actually, and we produce disease models on top of that. But that was just a proof of concept, because AI was not mature enough, and there were so many barriers to access and communicate between the hospitals, actually. And the trust was one of the major concerns, that even if people have a data, but if they want to share data, that people cannot access it. Even if they can access it, the data is there's so much noise in the data that they could not produce much value out of that. And then if there are a number of hospitals trying to find, say that if a consultant in one hospital and a consultant in other hospitals is trying to, for example, especially in other countries, trying to look into the same data to see what could be potential observations or diagnosis, there may be 15 to 20% a kind of difference in the decision making. So that was, to some extent, a big challenge that we wanted to deal with. This is one example where there's large data is distributed across hospitals. We want to use AI models to process that data to find something and that basically would help the doctors or the consultants in timely and efficient manner to support the decision-making process. Now, this is another aspect of where we are getting a lot of data. For example, whole genome sequences or targeted sequences, or even whole exome sequences. Especially, we are moving towards personalized medicine, and some people are saying that in next 15 to 20 years down the line, we will not be getting the same medicine if we are to have the same conditions. So, for example, if some, just excuse me for my naivety or simple examples, just to discuss the point here or highlight the point. For example, if 2 people have blood pressure, the blood pressure's reasons could be very different, one person, another person. So as a result, the medication that is prescribed would be quite different to individuals based on their genomic makeups, actually. So, and then the same could be the other diseases. So as we are heading into future, on this both navigation or diagnosis, as well as kind of whole I would call a kind of understanding of the disease would be becoming personalized. And to show scale of the challenge. So here, for example, each sequencing machine generates many gigabits per second, and there are thousands of machines. So, and all of this data is coming to data centers, and even, for example, in UK, we had a project, we say 100 genome project, or similar kind of name. So excuse me if it did not have the correct word. So, and they were just talking about 100,000 patients. And that was 300 million pound approximately, the cost that the government allocated. So the people are saying that by 2025 or even around that, so most of the data that's coming from different domains, so it would be genomic data that would be on the top of the list. So you could see here some of the number. They were saying that they would be having 22 exabytes. This was a PLOS Biology, that's 10 years old prediction, but still I think it's relevant. On the other hand, the YouTube is just 8, and Twitter would be 2.5, and astronomy that we are saying is 1.5. So you could see that how medical and life sciences are going to have an impact on the data that's available for research and analysis, because you could see that just in one area, and that's just sequencing or genome sequencing, you could see that the data is basically surpassing everything else that's there. So now how can we process that data to find something timely, efficiently, reliably, and in trustworthy way, so that we could help the medical professionals and the life sciences colleagues, and kind of help the society actually. And this is a big question actually, where AI is going to play a role. Now here, this is the example I was going to give you. So previously, that we had a one-size-fit approach to practicing medicine. So patients basically with the same syndrome most likely would be getting the same kind of medicine. But now essentially we are grouping them into patients with the same syndrome, and then this is a target tutor or targeted intervention, so that we could stratify those patients based on certain parameters. And let's suppose if we have 1 million patients, AI could simply categorize them quickly, and given that we have so much data behind it, and then we would be able to do it a kind of in a targeted way. And just think of a scenario that it's when you go to a GP, it is not does not take days or months to basically come to that conclusions. Rather, it's instant, it's real time. So as soon as we take the sample goes to a lab, results come back instantly, and then the AI models then help the decision-making process for the clinicians, and clinicians basically kind of prescribe the medicine. So that's essentially where both stratification and personalizations are facilitated through AI interventions. So, and now, that was essentially just an example of how much data we have and what could potentially be the application or use cases. Now, as people are saying that as we are getting more and more data sets, our ability to process that data is not growing at the same space. For example, this is a slide that I put together some statistics from IBM and Cisco. So this is that, so we would be having around 6,000 exabyte of data as we move into future actually. And 2012 we would have only the capacity to process 12%. It means that 88% of that data would not be able to be processed. Either we don't have the computational infrastructures, we don't have the AI models or automations, or we don't have the tools to process them. It means that as the time is growing, we are becoming to some extent naive or less informed about our own organizations, because we are generating more data than we could consume it. So, and coming back to the original point that the data is the currency. So if we don't know how much data we have and what's there in the data, so as we move into future, our ability to process that data would not be growing at the same pace as the data itself is growing. So we would be becoming less informed, and as a result, our competitiveness would not be matching with those people who have the ability to process that data. So the key message is that as the data is growing, we need to find tools and technologies and abilities or the skill set to process that data so that we could stay abreast with the modern trends and technologies. Now, the next part. So people have been using different type of models. So just here, so it's something is bothering me. I guess I should probably leave it. Yeah. So there are different AI model people have been using, and for example, here we say this is one of the approach people have been using. So where it's essentially we could say data-driven parallelism or distributed AI. So where people create a model. Let's suppose we have a model of AI. Someone has created an AI algorithm. Model is essentially an AI algorithm, actually. So, and we have 5 hospitals. So we created a network of those 5 hospitals. In each hospital, the same algorithm is executed or is running, and then we simply aggregate the results, and then we says that there are 5 patients of a particular disease who would potentially benefit from this intervention. For example, if there is a clinical trial going on, or if we are looking for potential interventions. So so here we don't create different models for different hospitals. Rather, the same model is executed, but all those models work concurrently and in a synchronized way to produce an output that is essentially statistically integrated in the end to give far larger a kind of cohort or information that would have been possible if this a model or algorithm would have been running in a single location. So here, for example, we have a convolutional neural network. We simply execute that. We give them a subset of the data, and in a subset of data could be a whole hospital data to a whole model, and we have X number of hospitals, and we were able to get results that are far more quicker, efficient, and both kind of rich in terms of volume and variety. So it's easier to implement. It has a stronger fault tolerance, and it gives us high throughput that's not possible if it was just running in one machine or in one location. So, and this is another approach that people have been using, where we divide a large model into chunks, and instead of whole model running in different location, we run those chunks into individual machines, and we say it basically a model parallelism. So just thinking of a scenario, previously in examples I was talking that we should have probably, let's suppose we have data for 5 hospitals, and each model is running in those hospitals. But now think of a scenario that there are so many individuals within the hospital. If they want to contribute their computers or their mobile phones and their other kind of devices into computational processing of the data, but then they don't have a large memories where gigabytes or terabytes of data could fit into. So what could we do is we could divide the whole data sets into chunks. We could divide the whole model or algorithm into chunks, and each basically chunk could be running into a device that could essentially accommodate or fit it. So in a way, we are using a divide and conquer approach where large models could be divided into pieces, and each piece is being executed in a machine and in a location that is appropriate for its execution. So it's good for scalability because everyone has mobile phones, and the approaches are easily scalable. It needs less memory. And so it means that if we could have a number of small devices that could get the same output, why not to achieve the same end goal at a fraction of the cost? Because cost is becoming a key kind of showstopper or key problem in scalability and large scale analysis of the data. That's not just simply medical sciences; it's the rest of the world as well. And there is another aspect that has been doing. A lot of people are talking about federated learning. Federated learning is that you don't share your data due to privacy and ethics and compliance reasons. So what people are doing is that, so if different hospitals or different pharma companies or different research groups, they're collecting their own data, they would not be sharing data with other organizations. Rather, they would run algorithms locally, and they would simply share the findings that they could extract from the data with the rest of the networks of AI models or AI algorithms. And we could say that it's a local execution. Data is not shared because everyone says that this is my data due to privacy and ethical reasons. They cannot share their data, but I could tell you that what are the key findings that our data is telling actually. So AI algorithm would be running within a localized environments and would be able to share the results of the execution, not the data itself. So this approach is becoming quite common due to different privacy and ethical reasons, because a lot of people are saying that AI would be intervening or infringing on our privacy and ethical issues. As a result, this AI models or privacy and kind of security conscious. So you would not be sharing data. You will not be sharing anything else other than the output of those algorithms. And then still you could control that what you share and what you cannot share. So, so I would quickly be moving on, because this slide, this is another example of a different scale where people are talking about in different parts of the world. It's not just, for example, 5 hospitals or 5 different countries. Here we are talking about 140 computer centers, and they're talking about 200 petabytes of the data. And different experiments are generating real-time data, and different countries are collaborating to achieve basically the results that was beyond the capacity of any single institute. For example, just think of a scenario that if all hospitals in the world create a consortium, start expanding, creating a network, and they may not necessarily share the data, but if we could see that in real time, they're sending that, oh, by the way, they found something interesting from their data. So my AI model is telling this. And if all the models are all the time kind of helping the clinical trials or discoveries and kind of a large scale analysis of the data, and this analysis being performed round the clock, almost in real time, you could see that how much we would help to medicine or the science in general. And this was one of the examples that the people have been doing, and I have been involved into this Large Hadron Collider at CERN. So a lot of discoveries that were made in LHC or in CERN are being used into the rest of in the science community. Either it's genome processing, for example, there is Elixir project that they're using it, or other great projects, for example, LCG and similar kind of applications into cosmology, into other areas that are benefiting from the development that happened in CERN. And why not medicine should be able to use this. So now, as we moved in the previous example that I gave, we talk about locality-aware schedule. So where the data is not shared, rather everyone is basically processing the data in their own localities and trying to find the results, more or less in real time. And I would not be spending a lot of time here because there's I want to kind of move on. But if you want to read more about the LCG and how basically different schedule and resource management model is working, I have given 2 references in the papers. So they are publicly available. These are my papers, and where we explain that approach, that how locality-aware scheduling could speed up the execution of AI models, or how AI could itself help to basically accelerate the data processing challenge actually. So this was another example of the same thing that here you could see that we had a project. This was then again the European Commission for a project, different kind of neuroimaging centers across Europe. We used to say it's a NeoGrid. And here in this particular project, we try to bring in different neuroimaging centers together so that we could provide an environment for neurology and kind of neuroimaging colleagues, so that if they want to find biomarkers or imaging markers of neurodegenerative diseases for intervention, for example, aging or Alzheimer's disease or dementia and similar kind of things. So here, previously, people used to run their kind of brain imaging models for Alzheimer's disease or dementia on individual machine, and it used to take hours and days. So what we did was we created a grid infrastructure between 3 hospitals, and the 3 hospitals here was Karolinska Institute in Sweden, Open University Hospital in Amsterdam, and FBFR Fatih Birni Fathi Hospital in Brescia, near Milan, so in Italy. And we tried to bring together more than 50,000 scans so that we could help the pharma companies in the speed up of this process. To first process individual brain scans, then find basically a kind of events of interest within those brain scans, and then try to create a statistical model so that we could see that what is the statistical significance of those findings related to the disease and for example, Alzheimer or dementia and similar kind of things. So idea was that can we create a Google for brain imaging that's AI driven, and then people could find more or less a kind of analysis at scale. And there was a follow-on project as well. We published some papers out of that, more on the computational side, not on the kind of medical output of those things. So you could read some of those things that we produced. And this initiative is still going on in a different groups. So, and then a number of follow-on projects also started. Obviously, this is one of the greatest application how AI could help humanity into future, for example, challenges. Either this is dementia or Alzheimer or other kind of mental health diseases, or neurodegenerative diseases. So, but here the challenge was that it was mostly a statistical learning. There was a less of AI that we say is AI today. It was more kind of statistical learning, working at a scale, but more or less getting the same outputs. So here you could see that we had a large neuroimaging workflow that is essentially we divided into tasks. Those individual tasks are executed in individual kind of workflow, individual machines. We simply consolidated the output, and we get the results. And we try to bring down the whole results from hours to few minutes, actually. So the AI algorithm, although it was, by the way, this was again a 10 years old project. So here we were trying to basically kind of accelerate the use of AI and in both imaging analysis and in general and brain imaging in particular. And we also published a paper that's there. It's mostly on what the technology we used and what type of AI we were using there. So just to summarize, this was mostly a kind of evolutionary algorithms. They were not convolutional neural networks or deep learning models. So, and they were obviously compute intensive, despite their the computing costs. We still kind of try to bring it down to many orders of magnitude in terms of performance and accuracy. So so then from 2005 onward, people started looking into a different type of AI. We say it's essentially deep learning or structured learning, actually. So here, people, instead of just statistical algorithms, statistical models, they started to create convolutional neural networks. Everyone is aware of what convolutional neural networks are. If you talk to a machine learning guy and say that they're using AI, behind the scenes, most of them, or 90% people, are in one form or another using convolutional neural networks. Here we divide a large input into different kind of kernel, we say, or into different chunks. and we then basically create different feature maps, and then we try to run different kind of iterations, and we say these are the convolution, and we then have a local analysis, and then the local features are merged into a global features. We say it's essentially fully connected layers, and there are almost 30,000 plus cells, and there are millions of parameters, and somehow this is some trial and error. There's no mathematical model that how these features should be interconnected, but behind the scenes with trial and error and experience, so people get almost 99.5 accuracy. So this is predominantly the model that even Google, Facebook, and other companies are using, but obviously a much more refined version of this as science has AI science has evolved to a large extent. So, for example, here I gave you an example of video stream analysis. People here a kind of acquire data, for example, through these different cameras, and those cameras could be scanners in hospitals. So just think of those scanners. We acquire those streams, and then individually we then push that into cloud storage, and then there are large scale kind of computational infrastructures. Either these are in memory or kind of GPU-based tools, and then we could see that, by the way, I'm looking for a particular scan. I'm looking for basically the output of particular analysis that executed on a number of those scans, and basically you could detect objects, or you could create a statistical validation of an object in a large cohort of objects or scans, actually. So we published a paper on this particular area, or on this particular approach, and you could read that in for more kind of depth. So, and here what we do is we have different camera feeds or scanner feeds. We detect targets, for example. Targets could be an individual tumor, for example, or it could be an object in a security camera, or it could be a particular region in a particular scan. Then we discuss the motion or the movement of those individual targets. That if, for example, it could be if it's a tumor, for example, how the tumor is progressing, and then we could create associations that how it looks like into the disease models. But this particular example was talking more from the security perspective, and that how different objects could move, but why not the same approach could be used to medical analysis and imaging analysis. So now there is a different challenge now. So previously, all the examples that I give, there were fewer devices that were generating data, and then we had a large scale imaging centers or computing centers or supercomputers that were processing it. But now things are changing. So for example, in up to 2010, there were 6.8 billion devices. Around 12 billion devices and 6 billion people. Now we have 50 billion devices and almost 7 to 8 billion people, actually. So now everyone is generating data, and our capacity to process that data did not grow, actually. So previously there were few data generators and there were few data processors as consumers. Now there are far more data generators, and the ability to process, both in terms of infrastructure and capability, did not grow that much. And that's the reason people are talking about that we need AI, and AI at a different scale that has a different velocity and volume and capability to process that. And this AI the decentralized AI or the distributed AI is the next thing to go, actually, because the scale and the size of both the devices and the population, because more or less everyone has a mobile phone, everyone is using Twitter and Facebook, everyone is using Google, everyone has to some extent the camera, every hospital has far more devices, and smart cars, smart homes. So there's so much data that we need to think of basically out of the box functionality to process so many data streams. And here, so it means that those challenges of centralized AI need to be overcome. So because there are more and more nodes being added to the network, we have too much data, latency is becoming big, and the cost or the transport cost is being, kind of complex as well. And when we have a large-scale network, resiliency or dependency or reliability is another challenge as well. So it means that we need to address those challenges in existing AI infrastructures before we could talk about that we are future ready. And then there are new type of applications coming. For example, remote surgeries or virtual reality or real-time surveillance or autonomous cars. So if we try to look into and reuse the existing models, they are not fit for purpose to deal with these kind of future applications. So it means that we need to think out of the box. We need to think of new models, and those new models need to look into kind of different architectural interventions, because those models cannot fit into the future applications. And that's the key focus of the research these days as well, because everything is instrumented, everything has an IoT device built into that around it, everything is streaming data, or those data needs to be stored and processed, but that need to be stored and processed more or less in real time. So it means that we need a different type of AI, and that AI is no more the traditional AI, that we need a more agile, slick, and smart AI that could process data more or less in real time and process at the location where the data is being produced. So it means that so previously all the data was being generated or captured at the source, and then all the data was being streamed to the data center. So it means that we were throwing or transferring or streaming so much data back to the data center. Now it's the other way around. So data is being processed where it's being captured. So, and we don't need to process all the data. Rather, AI algorithm should be intelligent enough to see that where the data is being captured, it should be intelligently kind of filtered so that we only process valuable data and we process it at the source, and the data centers that's collecting all the evidence and the data should only be storing fewer things instead of storing everything, actually. And that's essentially the key thing that we say. This is a third wave of AI, and which is edge enhanced learning. And here I give you an example. So previously we were storing all the data to the cloud. Now all those devices, for example, if we have scanning machines, if we have IoT devices, if we have smart cars, if we have smart cameras, all those becomes computers. So just think of a scenario, if we have 1 million scanning machines on 1 million cameras, previously they were just dumb devices sending all the data back to a data center, and then in the data centers, we were using AI algorithm to process. Now we need to embed that AI into those machines. So all of a sudden, those 1 million machines becomes intelligent machines. So we got much more capacity. We are using less of the network, and we are trying to have a much more kind of on-premises or kind of in-transit analytics. So those devices previously they were just producer of data. Now they are also consumer or extractor of intelligence as well. So this is the third wave of AI where everyone is trying to make those devices intelligent. Now smart cars is one example, or smart trains, or smart planes, and or smart scanning machines, or and all those devices are becoming much more powerful. And that's essentially going to play a major role in how we analyze the data and how we kind of extract intelligence. So, and if you look at LHC experiment, smart grid, smart car, genomics machines, and all those kind of other devices, they have similar kind of data rates and would benefit from the next architectural intervention in the AI that we produce. And we also published a paper here, and you could read that if you wanted to more details about this. So we also published another paper about the same thing, where we break down an AI model and run it at different locations or different sites, actually. So here we try to achieve the real-time AI analytics on a set of edge devices. So for example, if we have X number of genomics machine, we could try to basically embed AI into that, obviously, and this is just an example. Or if we have X number of video stream cameras or security devices or scanning devices or sensors, so the sensors could become intelligent machine, and we would process data, and then instead of sending all the data back to the data center, we are processing data on the devices. And here we are trying to create a smaller agile and slimmer AI models that run on the devices and basically and achieve the more or less same thing. So here we for example, you could see that we try to improve the accuracy, and it took 50% less time, and it saved us 99% bandwidth. So, and if you want to read more details, the details are in this particular paper. And here is another example of this as well. So here we not only process the data, we also compress data as well. So for example, if you're a scanning machine, instead of sending raw data, so AI is trying to compress data so that it only compresses the data that's required, that's just discarded. So here we created autoencoder models, and here basically you could see that instead of sending everything back to the data centers, we could cut down the data up to 99%. With less than 1% of the data, we try to extract the features, and those features are more or less the important features that lead to decision making. So for example, if there is a camera that's scanning everything, but instead of scanning everything, we should scan the relevant parts, and that's to some extent 1 or 2 or 5% of the data, and that data, if it's processed, would give us the same results that we were getting from the unfiltered data in the first instance. So this is another thing as well. So a lot of people are talking about adversarial AI actually. So here, if we have to learn, we should be able to think into the future that, oh, by the way, if something is not trained, AI model does not know anything, any data they will not be able to process. And if we don't have the data, we will not be able to get anything meaningful out of that. So if from the new inferencing or new kind of streams. So what we're trying to do is here, this is a kind of constant learning. If you just think of a ChatGPT, this is how it works actually. So, and we have been working obviously for a different application. You could see here remote condition monitoring and real-time anomaly detection, but the model behind that is similar to what the ChatGPT is. ChatGPT essentially says that you give a prompt and it learns from the prompt. I'm trying to give you the results. You are trying to narrow it down, and it's learning from your observation and your kind of intuition and your kind of interactions, and gradually it's refining. So, and it gives you the better reward based on your interventions, and eventually you get to the decision. And once you achieve a decision, you say this is okay, and then this becomes to some extent your final output, and that's stored. And next time you do the same search, you would get exactly the same results because the model has been learned. So, and here we did a similar kind of project with the different companies, and here we were trying to use it with the train companies, for example. So, and in the train companies here, you could see that so we are getting data from individual sensors, either it's a vibration data or motion detection or condition monitoring, and then the train is by the way, this data is being processed at the sensor level. So as the data is being retrieved, then we don't send all the data back to the data center. Rather, it's almost in real time. We are saying that this condition is being developed in this particular sensor. This train needs to go to the depot. Same could be applied to the humans as well. So for example, if there are sensors, and if those sensors could be deployed into individual kind of either care homes and others. So here, basically, we are trying to make more or less a kind of real-time interventions, obviously subject to compliance and ethical and governance issues, because obviously healthcare is far more kind of delicate in terms of both compliance and legal and ethical issues. So, and if we are able to do that, so then it means that those next generation devices could be intelligent enough to help the healthcare nurses and other medical staff in kind of either in the decision-making process or in monitoring process or in many other ways actually. So, and there is a big focus that some of these approaches could be used in the healthcare domain. And this framework, to some extent, this company that we have worked with, the company in Peak District to develop that. So although they're using it for windmills or trains and electric grids, but this could easily be used in the healthcare domain as well actually. So now, as we are moving into the future, so as you could see that we have many more devices. So there are millions and billions of devices. So can we, if for example, if I'm a human, I have millions of components inside my body. If there is a sensor that's capturing the information in each device, each component, can I created a virtual human from me? And that is essentially the fourth wave that we are talking about. We say it's a digital twins, and digital twin is essentially a digital replica of a physical objects, because there are so many data sources that they are integrated. So can we create a virtual kind of replicas of humans or organs? For example, a digital twin of a heart, digital twin of a lung, digital twin of a brain. So, and that's essentially driving the next generation of the AI. And we say it's the fourth wave that's taking. So, for example, here there are two things that are driving that. Other than sensors and AI, so virtual reality and augmented reality are playing a big role, because then we could visualize things in a way that was not possible before. So, and we could visualize things in our own operational environment. So we could touch and kind of look into individual aspects and see, by the way, the objects interact. And we could go into the future and kind of think of scenarios that were not possible before. So both visualization, both analysis, both information extraction, and the data itself is being benefited from the fourth evolution, or the fourth wave of the AI. Another other aspect that is driving the fourth wave is essentially the mathematical kind of soundness of the algorithms. Previously, it was a black box. AI is a black box. So you give data and somehow you get the results, but don't know and that how did you get the results. But people are now working with mathematical models, for example, how feature 1 and feature 2 are linked together, so that we could explain those models. We could have a mathematical governance and the compliance issues that are dealt within the digital twins. So, and that's another wave, another aspect or another development that's happening within the AI algorithms. More from the safety perspective, from the compliance perspective, there is a big safety summit in the UK, and the most of the kind of developments were that how can we use mathematical models to have a governance framework around AI, and that is essentially the fourth wave that's driving that. So, and this is what we are saying, that the digital twin is essentially a digital replica of a physical object, but behind that is AI. Those edge devices are basically kind of leading to kind of bring all the data, and then we're creating virtual models that are as good as the physical models, and then we could use it for different kind of intelligence purposes, for information extraction, and for future scenarios. For example, if we look at that, if we create a digital twin of a particular cancer, and we could see that how this cancer would evolve in 3 years down the line, 4 years down the line, we could create all those futuristic scenarios without having the interventions at this point in time. So, for example, this is an example of a digital twin where I took it from the public domain, where the oil drilling process, we creating the digital twin. All the key details could be handled in the lab before this goes into the production. This is another example of a digital twin where, for example, the whole kind of engines could be created in a digital twin before it goes into the production. So, so this is some of the experiments that we did. We used AI to produce the digital twins. For example, the whole jet compressors could be digitally twinned in 42 hours. Previously, it used to take 6 months to 3 to 6 months. Whole engines could be ideas that we could produce the whole engine or whole kind of lung, for example, digital twin within 24 to 48 hours, actually, because we have to process millions of these components, and we are trying to achieve it more or less in real time within the next 2 years. So that's the next focus of the work so far. And this is one of the last slides, that as we are getting billions of devices, and this AI is becoming distributed, there would be attackers that could poison the training set. It means that if we have noisy data, we have a low quality data, we were getting a low quality results, and that could basically kind of distort the decision making process as well. A lot of people are having a kind of issues about the safety of those AI models. So then, for example, how to guarantee the authenticity of the original data, how to guarantee the security of the data transmission, how to guarantee the fairness of the weight matrices. So, and this is a key problem. So adversarial AI is getting traction, because if someone gives us a noisy data or poison the data, then our results would be kind of impaired, and we will not be able to get the quality outputs. And this is a big focus these days. So it means the soundness of the AI models relies on the soundness of the data itself. For example, here you could see that we try to hijack a kind of a machine, and we simply extracted what type of data it's generating, and we could interfere with that. As a result, we were able to change the output of the machine, actually, because we interfered with the data, simply looking into the energy traces of that particular machine. And we published the paper that's available as well. So I would stop here, and just to conclude that the fourth wave, or the digital twinning of every physical asset, is going to play a big role. And you would see that maybe in 5 to 10 years down the line, we have digital replicas of the lungs or the heart or other organs. And eventually we would have a digital replica of a whole human, and then people would be using it for different interventions, for different clinical trials, for different for novel discoveries, either for either for disease progressions or therapeutic interventions. And we are already seeing those things. You would have seen that recently there have been cardiac digital twins. We are developing currently a lung digital twin as well, and some other people are doing different aspects, the physio digital twins as well. So it's many changes that's going to happen, and AI is going to play a big role. And I will stop here. Thank you for attending my talk, and I'm happy to answer any questions that you have.
Thank you, Professor. That was great. Thank you so much. I'll open the floor for questions. While people are writing their questions, or you're very welcome to raise your hand and ask your question yourself, and we could just take it on from there. And while I'll probably start with the first question. So you've given us quite a lot of insight of the examples, how AI is used in different scenarios, in different systems, including the healthcare system. And since we usually talk about and research and how the data is generated and analyzed, do you have an idea how AI or use of AI is affecting the publication process, or affecting in terms of how people produce publications at all?
Yeah, so that's a very good question. So, for example, one area where AI is helping is finding the relevant articles and trying to find the key aspects or the key messages from each articles, and then summarizing those number of articles into a nice kind of story. So here, if previously to write a paper, you need to summarize or see what's there in the state of the art. And if you need to read 50 papers to get to the conclusions, and it takes probably many months, AI may be able to do it instantly for you. And then instead of reading 50 papers, you may only have to read 5 papers actually, or 10 papers. And rest you could summarize the results. That's one way of benefiting or accelerating the publication process, because it could give you the outputs, or it could give you the findings that otherwise would have taken months. And yes, this is one thing. Then the second is some of the data analysis aspects. Previously, you have to run the whole experiments and you want to compare it. So now some of those things could be done for you as well, actually. So and other aspects of the proofreading and some of those things could also be could be helping you. And in some cases, even reviewers are using tools to write reviews, actually summarize. And obviously there is still oversight, and people are the human side, we cannot take it away, because obviously it would be unethical. But essentially, it's a decision support tool. We should not 100% rely on it, but we should use it for speeding up things, actually.
I do have another question, but I'll let other people ask questions first, and then. So yeah, does anyone would like to ask any questions or comments?
Hour.
Hi.
Sorry, can I'll ask the question?
Yeah, sure.
Let me just switch my camera on.
Yeah. Anybody else, if you would like to ask question, just please raise your hand, and then I'll be able to kind of see who is doing it, so that we all are not speaking at the same time, if that's okay. Yes, Lucas, please.
Yeah, Dr. Ashik, thank you so much for a very comprehensive overview. I was just thinking that was towards the beginning of your presentation. You talked about the ability to process data, and with time we will lose. It will be more and more difficult because the data accrued will be just increasing. And I was thinking, what about the quantum computing? Is it still in the realm of science fiction, or we starting to think about this approach to processing data? Because I'm thinking if that would be possible, then of course the processing data would be then much more easier than with no normal binary approach, isn't it?
Yeah. So you are absolutely right. And there is a lot of developments happening in quantum computing. Quantum is one of the key areas where government and funding agencies are focusing as well. But probably we are a few years behind. And even if we have a quantum computers today, that's not there. It would take a lot of effort to convert tools and technologies to benefit it from. So yes, it would help, it would speed up, but then those, for example, quantum computers would not help you to bring in the data from different devices. Quantum computing could help you if the data is there in the data centers. First challenge is you need to bring data back to the data center, and giving the ethical and compliance reasons, you may not be able to move data around actually. So it means that even if we have a quantum computer at a central location, this problem may not go away. So we could deal with the size of the data sets once it has been acquired and stored, but before that, quantum computer would not be able to help. And even if the quantum computer is there, and if, for example, in certain application, we need to make use of it or want to benefit from the quantum computers, we need to upgrade all the tools, mean software tools or the AI models, to get benefit of the quantum computers. And in this context, there is a lot of research and development happening right now. There are many quantum initiatives that the funding agencies, the government has introduced, and people are working on proof of concept models, both AI models. Quantum AI is getting traction, for example. Quantum software development kits are doing that as well. Quantum processing algorithms are being developed as well. So there's many software companies that are creating next generation tools. So this is very exciting time. In next 4 to 5 years, I think that production quality, small scale quantum systems would be in place. And obviously some of the applications that we are talking today would get benefit of the quantum computers, obviously.
Thank you.
Thank you so much.
Any other questions? Any other comments? I'm just conscious of time as well. Okay, so just one more question from me, and I'm trying to kind of think of more applying, kind of asking for an applied questions from the perspective of healthcare researchers or people who are interested in healthcare and publication process, etc. So use of AI, of course, it has got quite a lot of uses, but then in academia and in the publishing industry, people are quite also concerned about ethical issues around it, and some of which you could understand. But one of the things that we keep on hearing is that will the use of AI that much, where you use them to summarize the documents, essentially probably people wouldn't read that much. Is that going to dumb down humans and not push them to think a general kind of, people, and would have an impact on their ability to think critically and make decisions? What are your views about it?
No, I just think of AI as a next generation of the evolution of the computers. When computers were introduced, people were thinking the same. that it would be, for example, a lot of people were talking about IT and automation and all that, and people are thinking that this would take away the jobs, and it would make people dumb. Just think of a scenario if we didn't have email, when we didn't have the email and now we have the emails, what impact it has generated. Same is the case with, for example, people used to write with hands and then they started typing on the computers in Word. How how much impact it created, and many other examples. So computing overall has made us more productive, made us more smart, make it more, to some extent, kind of intelligent, and has more information at our fingertips that we did not have before. AI is going to play the same role as well. Obviously, there would be ethical issues, and people are already coming up with tools actually that would be telling that, is it AI generated output or is this the human generated output? So obviously there would be, for example, when people started writing assignments, students started writing assignments, they were submitting those, and it was very difficult that it's my assignment or someone else has written it or a tool has generated. Then we had Turnitin and similar kind of softwares. Now we know that from where it came and who has produced it. So, and AI is obviously moving in the same directions. There is a huge industry developing around it where you would be able to see that from where, what's the source of that decision, what's the origin of that kind of that input or output that AI is producing, and those ethical issues obviously would be dealt with. And this is an ongoing investigation. I agree that for the time being, there is not much in this particular area, but you would see that within months, not years, there would be many tools and technologies available that would be able to address these issues. And this, so ethical and compliance issues obviously are at the heart of the AI use. And this is one of the, probably we said, people are saying responsible AI or ethical AI or safe AI. So the safety, governance, and the critical kind of an analysis of what AI is producing would be at scrutiny as we move into the future. And I absolutely agree that on one side, we don't have framework at this point in time, but AI is simply going to move ahead with the next kind of developments, but then the governance and the compliance framework would also be developed. So yes, in both directions, there's a problem, and I'm sure that there will be solutions as well.
And in a way, it is here to stay. So I think it's better to learn how to use it properly and how to, and maybe what you're saying is that it probably is not going to dumb down people, but make them smart, probably in a slightly different way than what we are doing now. And it's evolutionary, basically, not
absolutely. Yeah. So if we don't adapt AI, we would be left behind. So the message is that it's going to impact every area. So especially where there's a lot of repetition or routine stuff. So for example, there will be less number of GPs that's required. A lot of note-taking process and analysis from the consultants or clinicians would be taken over by GP, so that the GP or the consultants and clinicians would become much more productive because they're spending 30-40% of time into writing and all those things as well. So all that bureaucratic stuff would be taken over by AI. All the data management would be done by AI. Compliance and ethical governance would be done by AI. So, and information extraction and finding would be taken over by AI. So AI is going to obviously kind of make things smarter, and that's one of the reasons probably you saw that government has made a big investment into NHS. So where they are trying to use AI tool to make the people more productive there, efficient there, because they think that by just giving more money, it's not going to solve the problem. Rather, making people more efficient would
intelligent solutions.
Yeah, and that's the reason they're investing a lot in AI, and especially the healthcare and NHS.
Great, thank you. If we don't have any other comments or any other questions, I would like to thank everybody for joining us today. And I would like to thank Professor Anjum for a very interesting and useful talk today. And yeah, thank you so much, everybody. And do give us your feedback and any questions, and we will share with the recording with all the participants who have registered. So we may come back to you if they have any questions. We'll direct it to you, if that's okay. Thank you ever so much.
Thank you very much for inviting me. Thank you.
Thank you, everybody.